Okay, welcome back again. This is going to be episode number 32 of Learning by Doing MPI, and this is going to be part number 4 of Visual Topologies in MPI. So we're going to continue from where we left off, basically. We already talked about those topology constructors, and we said that generally we have 3 types of those virtual topologies. One is Cartesian grids or Cartesian virtual topologies, and then we have in the general case, we have graphs, and then in the most general case, or the scalable one or the efficient one, we have these distributed graphs. So now we're going to work with inquiry functions. If a virtual topology has been defined with one of the above functions, those constructors, so the topology information can be looked up using inquiry functions, and they are all local calls. So this is also important. The first one on the line is MPI topo test. So we might have been using these in different examples, but we're going to see one example at least of usage of these functions. For example, in this case, we have MPI cart create, which we have seen this example before. MPI cart create. Let's see. And before jumping into that, let's see what kind of arguments does it get. So you got to pass in your communicator, and then it basically dumps out a status for you. That's an output. And that status has basically the information about the topology of the communicator that you're working with. That status is going to have these possible values. Either it's going to be a graph, either it's going to be a Cartesian grid, or it's going to be a distributed graph. Or if no topology information is associated to that communicator, then it's going to basically pass you MPI undefined. So let's jump into this. Here in the inquiry sections, previously we haven't talked about these. We said that we're going to skip them until the right time comes, and now it's the right time. So we have a status integer, and then we pass basically this status integer to MPI topo test, and then only the root process basically checks whether the status is MPI Cartesian, and if it indeed is, then it's going to print cart.com is actually a Cartesian communicator. So if I say MPI MPI cart create, let's see, and MPI run minus NP12, I think it was 12 processes for this example, then you see that, yeah, it says cart.com is a Cartesian communicator, right? Okay, the next one on the line, I kind of don't understand this because the standard starts with Cartesian grids first, and then it goes to graphs, and then it goes to distributed graphs. But when it comes to inquiry functions, it starts with graph dims. I don't know why there's sort of maybe inconsistency or something like that, but it starts with MPI graph dims get, which only works with MPI graph create generated graphs. So you cannot use this sort of function with distributed graphs. Only it works with MPI graph create generated graphs. Then we have an example, see MPI graph create for this one. MPI graph create. Okay, in the inquiry section right here, we have, okay, let's see what it gets. You got to pass in your communicator, and it's going to dump out for you the number of nodes, which is the number of processes you have in your graph, and then number of edges, the number of edges you have. So as simple as that. And here it says that the functions MPI graph dims get, the one above, and MPI graph get, the one below right here, retrieve the graph topology information that is associated with the communicator. So these two functions can be used hand in hand, and I'm going to show you in a second. The information provided by MPI graph dims get can be used to dimension the vectors index and edges correctly for the following call to MPI graph get. So MPI graph get, you see that it needs index and edges as output to basically put the indices and edges for you. But for that, it needs to have correct sort of sizing of those arrays. And for correct sizing of those arrays, max index can be taken from MPI graph dims get, and also max edges can be get from the edges output of MPI graph dims get. So these two functions, as I said, they can be used hand in hand, and you see here number of nodes, number of processes, number of edges, and then we use this MPI graph dims get. You pass in your graph communicator, number of nodes, and the number of edges, and those we haven't initialized them, but it's going to get populated with this sort of function. And then the root process is going to basically print you that the graph communicator has this number of processes, or this number of nodes, and then this number of edges, and we pass in those two variables. And then next to that, we have the proper sizing for the indices, and that's going to be a number of nodes, and a proper sizing for the return edges, that's going to be the number of edges, and we use MPI graph get, we pass in all those things. We haven't initialized these two arrays, but they're going to get populated with this function, because all these three factors or all these three arguments are going to be inputs, and these two are going to get populated within this function. And then a rank process, only the root process is going to print some information about how many sort of, what is the index or what is the edges, how many sort of cumulative process structure do we have, or I don't know, it contains the following edges. It gives you also the edges. So if I say MPI CC, MPI graph create.c, and if I run it, not with 12 processes, of course, I think it was 4, right? Yeah, here you see that it says we have 4 nodes or 4 processes, and then we have 6 edges, and you see that the indices look like this. This is a cumulative number of neighbors that you have. So we have 2 numbers, now we have 3 numbers, now we have 4 neighbors, sorry, not numbers. And then 4 plus 2 is going to be again 6 neighbors. So there we go. That's what we get as an output. And then the last thing here is basically printing you a flat version of those neighbors, which is 130302. The pattern is 130302. That's exactly as before that we had. The next one on the line is MPI cartdim get. Now we move into Cartesian inquiry functions. Again, we go back to MPI cart create. When MPI cart create, let's see, what was the name of it? Cartdim get, cartdim. So we used it right here after the topo test. Now we use, let's see what it gets. You got to pass in your communicator, and then it gives you basically how many dimensions it has. It's an output, and you see that it's an int star, so it's an integer. So you pass in the address of your return dims, and root process is going to say how many dimensions it has. The next one, so this is the cousin of basically MPI graph dims get. You see that there's an extra S for graph version of it, graph dims get, but this one is cartdim get. And the corresponding extra sort of information about the Cartesian topology you can get with MPI cart get, similar to what we had with MPI graph get. So again, the functions MPI cartdim get and MPI cart get return the Cartesian topology information that is associated with the communicator. If com is associated with a zero-dimensional Cartesian topology, then MPI cartdim get is going to return U0, and MPI cart get is going to return these values unchanged. So you see that the first 2 values are going to be the inputs, the communicator, and the maximum dimensions. In order to be sure that you're not making mistakes in how many dimensions you have, try to make sure to use these 2 functions hand in hand. So use the output of this MPI cartdim get and pass the output of that one in as the max dims, because it gives you the number of dimensions. And then you got to pass in properly sized of dims, periods, and chords arrays, and those are going to get populated in this function call. So that is what we have here. So properly sized, it means that we use the output of this cartdim get as the size of that arrays. So that's dims list. So that's number of processes in every direction. Then we have periodicity information. Then we have coordinates. Then we call this one, and then the root process is going to print some information for us regarding the number of processes in every dimension, respectively. That is taken from this return dims list. And then you're going to print some information about the periodicity information in every dimension, which we didn't have one, so I assume to get basically 0, 0, 0 for every dimension. And finally, it says that root proc has the following coordinates, and the coordinates, since we are dealing with a 3-dimensional structure here, then we're going to have 3 values for every coordinate for 0th, 1st, and 2nd dimensions or directions. And then we did sort of the same, but slightly different with rank of 5. We did it with rank 0, but with rank 5 as well, because we wanted to use some other functions that we're going to see on the line. For example, this MPI card rank, we haven't seen that one. And MPI card chords, we haven't seen that one as well. So let's see this one in action. So you see the output, right? MPI CC. Let me do it again. Or maybe I should clear the screen first. MPI CC MPI card create.c, and we should run it with 12 processes because this is a different example. Then you see that it has 3 dimensions, and then it says that we have 3, 2, and 2 processes in every direction. Multiplication of all of them is going to be 12, the number of whole processes we supplied here. The periodicity information, since we didn't have any periodic conditions, it's 0, 0, 0. And then we say that root proc has the following coordinates. That is what we had right here from this returned chords. Now we go next one on the line, which is MPI card rank. This is what I was talking about in rank 5. We said we use this one. So you're going to pass in your communicator, you're going to pass in your coordinates, and then it gives you basically the corresponding rank. In that case, since I use the return coordinates, so I already basically know that my rank 5 or the process number 5 knows its own coordinates, then I use this return coords as sort of the input here for MPI card rank. And then I say rank of process 5 because I already know that with this if isolation case that process 5 is going to release or execute this information, then I know that it's exactly process 5. So I say rank of process 5 is the return rank which I pass in to this function MPI card rank. So let's take a look at the output. It says that proc5 has this following coordinates. This is the information we printed before that. That is 1, 0, 1, and it's also in agreement with what we had here, with what we printed here. Proc5 has in MPI com world has this Cartesian coordinates 1, 0, and 1. Same information here. And then we said rank of proc5 is 5. But since this thing, take a look at this. Whatever I supply here, it's going to have information about that. So if I, instead of this return coordinates, if I say, I don't know, test coords, and I say this one has, let's say, 3, because we have a 3-dimensional case, and then I supply, for example, the information about the root process, and then I use, instead of this return coordinates, I use this test coordinates. You see that you should ignore this one now. This is not proc5 actually, it's going to be proc0, right? So I'm going to save that. I'm going to run it again, compile it and run it, and then you see that rank of process 0 is 0. So you can pass in any coordinates you want, and then it gives you any information you want. So it doesn't necessarily means that if I have this isolation rank 5, then I can only inquiry about process 5. The next one on the line is sort of the reverse of this MPI card rank. Here you supplied the coordinates you wanted, and then you got the rank back. And in the next one, MPI card chords, it's going to give you, you're going to supply the rank, and then it's going to dump out the coordinates for you. But I forgot to mention something right here. This paragraph is basically saying that if you have periodic conditions, then things are going to work a little bit different. So here, imagine that I put, let's say, -1 here. So this means in 0th direction, I'm going to go 1 back. But since I don't have any periodic condition right now, I'm going to add periodic condition for the 0th direction because I want to go back 1 step, -1, right? So let's do this. MPIC, by the way, this is not proc0. Maybe I should have removed that one, but let's see what it happens. So you see that it says rank of proc0. So ignore this proc0 because this is something which we statically printed. But what we get here is actually 8. Why rank 8 is printed here? The reason for that is, take a look at process 0. It's 0, 0, 0, minus 1, 0, 0. Since we have periodic condition, it's going to be, we had 3 dimensions for the 3 processes for the 0th direction or dimension. So this means that this is going to go periodically back to number 2, because 3 processes is going to be 0, 1, 2. And then so this should be 2 and corresponding 0 and 0. So if you take a look at that, this is it, right? So this is going to be the periodic sort of neighbor when we go one step back with -1. And you see that this corresponds to process 8. So that is the rank of that process, which is returned into that when we use this MPI cart rank. So that's everything this paragraph basically says. Now you sort of understand. If you have periodic condition, you go out of bounds with your coordinates. So what you supply is your coordinates. And if you go out of bounds, then it adjusts it with those periodic conditions. So that's it. The next one on the line is MPI cart coords. It's sort of, as I said before, it's sort of the reverse of the previous version of that function. You got to supply your rank, and then you got to supply the maximum dimensions, and then it dumps out the coordinates for you. In this case, let's go back here. I can keep these here. I didn't want to, or maybe I should remove them. I take the periodic condition out, and I take also the test coords out, because I want to keep my codes intact. Those changes was only for you to understand these things. And now the next thing on the line, I'm going to save that. Next thing on the line is MPI cart coords. You see that we passed in the Cartesian coordinate, and then we passed the rank, which is rank 0, and then we say return dims. That's the maximum dimensions. This is the length of vector coords in the calling program. They're going to dump out basically the coordinates. And then we say proc 5 knows root proc has the following coordinates. So again, similar to what we did here with MPI cart rank. We said that not only we can ask with the coordinates of process 5, but you can supply any coordinates there, and then it's going to give you the corresponding rank. And here also process 5 is not giving the coordinates of its own, but it's giving the coordinates of the root process, because here we supplied basically rank 0. And if you compile and run it, you see that it says, hopefully, let's do it again. I think it's better. If you do it again, it says, okay, proc 5 knows root proc has the following coordinates, and those coordinates are 0, 0, 0. That is why we supplied those information right here as rank of 0. If I would have supplied here the rank of 5, then it's going to give me then it's going to give me 1, 0, 1, and the reason for that is proc 5 has these coordinates 1, 0, 1. Again, I go back and I change it back to 0 because I want my codes intact. Okay. And then we have the inverse mapping, rank to coordinates translations provided by MPI cart coords. If cum is associated with a zero-dimensional Cartesian topology, then coords will be unchanged. If max dims is less than the number of dimensions of the Cartesian topology associated with communicator cum, the outcome is unspecified. We already talked about this before. And then the next one on the line is MPI graph neighbors count. So this one only works with MPI graph create generated graphs. Again, we got to go back to MPI graph create. We have seen this. Let me clear the screen maybe. MPI graph create.c. And then we have this count, boom, right here. What kind of arguments does it get? You got to pass in your communicator, you got to pass in the rank, and then it's going to give you the number of neighbors that you have. Number of neighbors specified of a specified MPI process with the rank that you supply right here. So in this case, we said getting neighbors, number of neighbors. We passed in every process basically pass its own rank here, and then it's going to get the number of neighbors that it has. But you see that this gives you the count or the number of neighbors. Then you have one sort of cousin to this one, which works hand in hand with this one. That is MPI graph neighbors. This one is MPI graph neighbors count. This one is MPI graph neighbors. So it doesn't have that count in the end as a suffix. But what you need to supply here is the communicator, the rank, and then maximum neighbors, which you can use. This is size of array neighbors. So with this information you can get from the previous function, basically. You can supply it from that. And then you can pass in an array here. You see that the neighbors is an array. If you pass in an array there with the proper sizing, it's going to basically dump out those neighbors that you have. In this case, every process figures out how many neighbors it has, and it tries to basically put neighbors into with the proper sizing of number of neighbors, and then we basically print some information about those. So MPI CC, MPI graph create, and we have seen already the output of this one. Oh, we should use MPI run minus NP. I think it was 4, right, if I'm not mistaken. Yeah. So this is how basically it works. We say it has this many neighbors, that is num neighbors or n neighbors, and the actual neighbors are basically dumped out with what we get from here. So the first one is the rank. This process has how many neighbors? That's what we get from MPI graph neighbors count. And then every process basically goes through this loop to basically print the neighbors, the actual neighbors, which we basically filled it up with MPI graph neighbors. Okay, there's some information regarding, I don't remember what is this, but let me see. Try with example 8.2. Oh, I do remember now. Okay, let's read the paragraph first. MPI graph neighbors count and MPI graph neighbors provide adjacency information for a graph topology. The return count and array of neighbors for the queried rank will both include all neighbors and reflect the same edge ordering as was specified by the original call to MPI graph create. Specifically, MPI graph neighbors count and MPI graph neighbors will return values based on the original index and edges array passed to MPI graph create. For the purpose of this example, we assume that an index -1 is 0. And why do we have index? Why does it say that index -1 should be 0? The reason for that is the number of neighbors or n neighbors returned from MPI graph neighbors count will be index rank minus index rank -1. And if you pass in rank of 0, so index of rank 0 was 2, right? If you remember, it was 2. But this is going to be 0 minus 1, so it's going to be index of -1. So here it says that for this purpose, we're going to consider that that value is going to be 0. So index of 0 is going to be 2. So it says that the process 0 has how many neighbors? It has 2 because index of 0 was 2. Let me show you. So that's the index of 0 right here, 2. 1 and 3, it's 2. So that's the index minus 0 is going to be 2. And that's true. Process 0 has 2 neighbors, and those neighbors are 1 and 3. And the neighbors array returned from MPI graph neighbors will be edges of index rank -1 through edges of index rank -1. And then I said here, whoops. So the 25 minutes is over here, but I'm going to finish this example and then we're going to continue with the next episode. So I said try with example 8.2. That means, let's say we're talking about rank 1 in this case, because I don't want to have -1. So if I say rank 1, it's going to be index of rank -1 is going to be 0. Index of 0 is going to be 2. Edges of 2 is going to be the third value in edges. So take a look at this edges. The third value in edges is going to be 0, right? So that's the neighbors. And then the next one is edges of index 1. Index 1 is 3 minus 1. So index 1 is 3. Minus 1 is 2. So it's going to be edges of 2. So edges of 2 is the third element, which is this one. So what does it mean? So it means this through this. In this case, these two are the same. So it means that we only have one neighbor. And simply, since the initial rank we chose was rank number 1, then we know that rank number 1 has only one neighbor, and that is process 0. This is basically what here it says. Okay, and then we have this topology information. We had a separate example that specifically reflects whatever we have in the standard example. We said see MPI graph topology inquiry, but I forgot that the time was over. So I'm going to stop here, and then we're going to continue in the next episode.